All right. Excuse me, I'm sorry. So starting with 12.2 in scatter plots, let's look at the definition of function plots, and we'll follow that up with the definition of a scatter plot. So a function plot is a little bit of review from algebra. So in algebra, trigonometry, pre-calculus, and calculus, one typically starts with a function in two variables, x and y. The function defines the relationship between the two variables, x and y. X is the independent variable and y is the dependent variable. Okay, so what I said here up above is that we start with a function in two variables, x and y. So this is an example of a function. Now, the reason why it's describing a relationship is that this is an equation. Okay. The relationship comes from the statement in this equation that y is equal to some value of x. So if you put in a value of x, it's going to output a value of y. That's the relationship. Um, so this is showing that y is related to whatever value x happens to be. And because we don't know exactly a specific value of x, we use the variable x as like a placeholder for that value. Maybe not a placeholder, but more of a container. So typically, when we're talking about a function plot, you start with a function. So you start with an equation like this. Now, from this equation, um, if you know some algebra tricks, you can take that equation and you could right away go ahead and make this line. Okay, not the individual points, but the line itself. Let me switch that to, you could actually draw this line because this 2 at the end, this is called your y-intercept. That's where this equation intersects the y-axis. And you can see right here on the y vertical axis, it intersects it at 2. And then we have this, our variable x, and in front of the x, you don't see a number there, but essentially that is the number 1. Because 1 times anything is just that thing. It doesn't change it, right? We could have 1 times 2, and that's 2. We could have 1 times 31, and that's 31. So multiplying any number or variable by 1 doesn't change it. So instead of having just an x, we can think of this x as having a 1 in front of it, and we don't change the original value. And what that does is this tells us that we have a slope of 1 on this equation. And, slope is kind of what you would think of if you're at the base of a mountain. The slope is the rise of like the side of a mountain over its run. So slope is rise over run. And from this function that you've started with, we know that we've got a slope of 1, which means that starting from our y-intercept, we're going to have a rise of 1 and a run of 1. We're going to have a rise of 1 and a run of 1. We're going to have a rise of 1 and a run of 1. Rise of 1, run of 1. Rise of 1, run of 1. And we could go forever, okay, and just keep going in this direction and we could keep going in this other direction. And we would just end up with a line that just extends forever into positive and negative infinity. Okay, so we could just graph that function that way. But one of the pluses of starting with a function is that we can use it to get some ordered pairs. So what are ordered pairs? Ordered pairs are specific values of x and specific values of y that are related to that value of x. So, so for example, if we wanted to let x equal 1, that is our input. So we would let x equals 1. So we would take 1, we'd substitute it in there for x. And so we're going to have y equals 1 plus 2. And what's 1 plus 2? 3. So in this equation, if x is 1, then that means y will be equal to 3. Or said in another way, 1 is related to 3. And that gives us a relation of an ordered pair of an x and a y together. And you'll notice that this point, this ordered pair, where x is equal to 1 and y is equal to 3, if we were to plot this on our graph at the point of 1, 3, where x is equal to 1 and y is equal to 3, we get exactly this point right here. If we wanted to see what value of y is related to an x value equal to 2, then we just go through the same process. We would take 2 and we'd plug it into x. And 2 plus 2 is 4. So 2 is related to 4. That gives us the ordered pair 2, 4. And if we plot that, that's going to be 2 on the x-axis and 4 on the y-axis. If we do that again with 3, we'll get the point 3, 5. So 3 on the x, 5 on the y. If we put in 4 for x, then we get 6 on the y. So you can see we're coming up with these ordered pairs based off of the function that we started with. And this is, a very common thing that you see in algebra. All right. And these ordered pairs follow the same line that we sketched earlier just by looking at the function itself and just graphing it with some tricks that we know. Okay. I'm sorry, this is not deleting like I wanted to. Try this again. Doesn't work this time. Ooh, that didn't work. Okay. All right, so I'll just keep going. Okay, so a function plot means that we start with a function and we end up with a two-dimensional graph. Okay, and I kind of showed you a little bit in detail about how we go from a function over to a graph, and we can use ordered pairs to get there. Now, with a scattered plot, it's a little different. It's in the opposite direction. So again, with a function plot, the function is known and the ordered pairs are unknown, we have to find those ordered pairs. But with a scatter plot, the ordered pairs are known, but the function is unknown. So we need to figure out what is this function that goes through these ordered pairs that we know. So a scatter plot is your first look at the shape or pattern of the data that was collected. If there's no shape or pattern, then that means there is no relationship between the two variables. And how we say that in statistics is we say that there's no correlation. So if there's no shape or a pattern, then there's no correlation. If there is a shape or a pattern, then a relationship exists between the two variables, and we say that there is a correlation between the two variables. So with a scatter plot, we collect some data of two random variables. So it might be the time to complete an exam is one random variable, and the resulting exam score is the second random variable. So one student took 77 minutes to take the exam and got a 51.8% on it. Another student did the exam in 35 minutes and got an 89.1. Another student completed the exam in 47 minutes and got a 40.9%. So we can take all of those ordered pairs, okay, because these are ordered pairs where time is on the x-axis and the exam score is on the y-axis. And that generates a scatter plot. So we have time to completion on the x-axis, and we have exam score on the y-axis. And let's see here, that point of 7751.8, so this first one here, this first ordered pair, so that would be 77 on the time to completion. That would be somewhere right about here. And 51.8 is just going to be above 50. So I believe it's this point right there. So that ordered pair, that data point on our scatter plot is represented by this student's time and exam score. And so you see we've got an entire class represented here. And this is the shape or pattern for students in a class and their time to complete an exam versus their exam score. And from these ordered pairs, we can find a function that's a best fit. So you'll notice what was different here is that these points don't line up perfectly on a straight line, okay, like they did up here. Up here, our ordered pairs fell exactly on a straight line. Well, the reason for that is we were starting with a function to begin with. But now with scatter plots, we don't have the benefit of starting with a function. We have to start with ordered pairs. And these ordered pairs, we're collecting this from the real world, and the real world is chaotic and random and messy. So there's going to be some variation there. But what we can see in this data, there is a pattern. The pattern is that we've got this downward sloping line down to the right that appears to be a best fit to the data. And this line is going down and to the right. Right? Starting from up here, it's going down and to the right. Or said another way, as the time to completion goes up, then exam score goes down. So as it takes a student longer to take the exam, the lower their exam score. So you can kind of see that, for students that took a little less time, who maybe, felt very confident with the material, they were able to kind of do it all and do it confidently, and therefore do it quickly. They ended up with a higher exam score than maybe the students who didn't know it as well and spent a lot more time on the exam trying to figure it out as they were taking it. And so they ended up getting a lower score. But in the distribution of these data points, there is a linear trend, and it seems to be going down and to the right. So now that we've got this linear trend, we can find a mathematical definition of that linear trend. And this is the mathematical function that defines it. Take that off. Okay, so it's y equals negative 0.72x plus 108.54. So you'll notice that what's a little bit different about this line is that this one has a negative number in front of the variable x. And that negative number means it has a negative slope. The slope is going down and to the right. Okay, so that's what a scatter plot is. A scatter plot is starting with two random variables, creating ordered pairs between those two random variables, and plotting them. That's a scatter plot. Okay. Now, scatter plots, can end up being linear. Okay, so like our example, it looks like there's a linear trend to the data. The data could be nonlinear. So for example, it could be normal, meaning it looks like a normal distribution. Could be something like that. Or there could be no pattern at all. So, it doesn't really look like you could draw a line through these data points that looks like that, and it appears to fit them. Or you could draw a line through them like this, or like this. There's no clear linear pattern to this data. And so because there's no pattern, you would say that there's no correlation between the height, maybe the height of a person versus relative frequency of protein that a person consumed. Okay. So note that, nature is complex and random, yet it is understandable and predictable. Complexity and randomness is expressed in the scattering of the data around the central line or curve. So this scattering of these data points around this linear relationship, is that comes from the complexity and randomness of nature. Data from nature, more often than not, looks scattered and not perfectly aligned like a function plot. The linear scatter plot above was taken from one of Dr. Morales's class exam results. What factors played a part on student performance and how long it took. So I talked about that a little bit a few minutes ago. Okay, so next I'd like to talk about maybe formatting scatter plots. But I think for now, just stopping this, talking about the difference between a function plot and a scatter plot. We're going to be working with scatter plots here in chapter 12. So I think this is a decent introduction to what they are. All right, let me know if you have any questions.